Now that we've finished talking about the basics of valence shell electron pair repulsion theory and all the different types of molecular geometries we can have, the next thing that we can add to our discussion of thinking about molecular geometries, and one of the properties that's really important in, that we can understand from molecular geometries, is the idea of molecule polarity. We've already introduced this idea that covalent bonds can sometimes be an unequal sharing of electrons. So this was the idea we talked about in Chapter 8. Thinking about something like a molecule like HF, where we use the idea of electronegativity to tell us about how much the different sides of a molecule are going to pull on electrons, right? Fluorine being our most, highest electronegativity element in the periodic table is going to preferentially pull electrons towards it in a covalent bond like this. So we can indicate that this with this dipole moment arrow, or we also have used these D plus, D minus with the little lowercase deltas to indicate this polarity. So when we're just thinking about a single bond or two atoms, this is pretty straightforward. HF, we looked at several other types of bonds. But what about in a molecule? And why does this matter? So let's think about, and why does molecular geometry matter with this? So let's think about a couple of molecules. We'll first start with carbon dioxide. All right, so CO2. Two molecules, we're going to look at CO2 and H2O. So carbon dioxide and water. And the differences between these molecules lead to some of their properties that we observe about them. Okay, so in both of these molecules we have polar bonds. These are both polar covalent bonds. They involve oxygen, which is a quite electronegative element. And so in both of these, if we look at just the oxygens, both oxygens are going to preferentially have the negative charge, or all three, I should say. And then our other elements, our other atoms, are going to have the positive charges. Okay, but what shapes do these molecules take? Well, we've looked at carbon dioxide, and this is a linear molecule. It has two electron domains, and so therefore this is linear. Whereas water has a tetrahedral, because it has a steric number of 4, has a tetrahedral electron pair geometry and a bent molecular geometry. Right, so these both have 3 atoms, but their shape is different. Carbon dioxide is straight, whereas water is not. So let's think about the dipoles involved here. So I'm just going to redraw these over here. So because carbon dioxide is in a straight line, we could draw our dipole moments. The positive side is going to be on the carbon, and the negative side is going to be on the oxygen, so we can draw them like this. Now, when we're thinking about these dipole moments, they're going to add together in 3-dimensional space. So if we think about these arrows sort of adding together, we overall get a net 0 dipole. So basically, we're going to have a negative charge over here, but it's going to be balanced out by a negative charge over here. And so the overall charge on the whole molecule is 0. And this overall displacement of electrons, this overall charge disparity on a molecule is what we call the dipole moment. And carbon dioxide has a dipole moment that is equal to 0. So this is what we call a nonpolar molecule. So there's no net charge because the 2 negative charges cancel each other out. The key here is that this molecule has symmetry, meaning that the oxygens are equal and opposite to each other and lead to this nonpolar behavior. And this means that carbon dioxide is not very good at dissolving things. And it's part of the reason, not the only reason, but part of the reason why it's a gas at room temperature. And we'll get more into that in the next semester as we talk about intermolecular forces. So the fact that carbon dioxide is nonpolar has lots of consequences. But let's look at water now. And so similar here, we have 2 bonds that have similar polarity. Right? So if we look at OH2, H2O, water, we're going to have positive charges on the hydrogens and negative charge pointing towards the oxygen. But if we add together these arrows, we can see that along this axis here, the charges are going to cancel out just like they do for CO2, right? So But if we're thinking about this direction, from the top to the bottom molecule as I've drawn it here, these arrows don't cancel out. In fact, they add together a little bit. And so what we get overall is we can draw that the dipole moment, right, so water is polar, and the dipole moment goes from about here in between the hydrogens pointing towards the oxygen. So water is polar, and that leads to a lot of consequences for water. Water, because it's polar, is very good at dissolving things, particularly other polar things like ions, and so that's why we think about solubility of ions in aqueous solutions. Water is a very good solvent, meaning it can dissolve lots of different kinds of things. And one of the big reasons for that is because of this polarity in water. All right, and so we could say that the dipole moment is non-zero, and we can actually quantify this value. So dipole moments are given in units of debye. Give myself some space here. And that's written as a capital D, and this has a specific meaning, which is 3.34 times 10 to the minus 30th coulomb times meter. We're not really going to use this a whole lot, but just so you know what this is in case you're curious. But in these units, water has a dipole moment that's not zero, and it's equal to 1.85 debye. Now, how do you measure this? You have to have some sort of way of producing an electric field that causes the molecule to orient with that electric field. So you have a positive and negative charge, whether it's on some plates or something, that causes the molecule, it will then orient itself. And that's one way to tell whether a molecule is polar or not, besides just looking at the geometry. Okay, so this is our first couple of examples. So in the next video, we're going to continue this discussion, look at a few more examples, and talk a little bit more about molecule polarity.